0, 1, 2.
To understand forced induction, we must start with the standard internal combustion engine. In its baseline state, it relies entirely on atmospheric pressure. As the piston drops, it creates a vacuum. But that vacuum can only draw in as much air as the local atmospheric pressure is physically able to push into it. Because of this limitation, an engine's maximum air intake is strictly dictated by its displacement, the literal, physical volume of the cylinders. Once that air is mixed with fuel and ignited, the piston is forced down, creating power. But the cycle immediately follows up with the exhaust stroke. As it pushes back up, it violently forces the hot, expanding exhaust gases out of the tailpipe. A massive amount of energy is lost. This creates a rigid engineering dilemma. For decades, if you wanted to burn more fuel and generate more power, your only option was to build a physically larger, heavier engine block to capture more air. Atmospheric pressure is the ultimate bottleneck. It traps naturally aspirated engines in a strict, inefficient size-to-power ratio. Breaking that atmospheric bottleneck didn't begin with sports cars. It started in 1905, when a Swiss mechanical engineer named Alfred Büchi patented a highly supercharged combustion engine. Büchi wasn't trying to set automotive speed records. His goal was to maximize the efficiency of stationary industrial power plants by recovering their wasted exhaust energy. By the 1920s, this technology saw its first major commercial success, bolted onto massive marine diesel engines. Engineers quickly scaled the system up to handle the immense volume of exhaust gas generated by giant German passenger ships crossing the ocean. During World War II, engineers mounted turbochargers onto aircraft like the B-17 bomber, proving their aerodynamic value by maintaining power output at extremely high altitudes. It took decades for the engineering to be successfully miniaturized, finally arriving in consumer production cars like the Oldsmobile Jetfire in the early 1960s. The modern turbocharger is distinctly industrial in origin. It is an energy recovery tool, heavily modified over decades to weaponize waste exhaust in passenger vehicles. This diagram reveals the two-sided architecture of a turbocharger. Notice the strict division between red exhaust components on the right and blue intake components on the left. On the exhaust side, hot gases exit the block through the manifold and route into the turbine inlet. Rather than venting safely out the tailpipe, the rushing exhaust transfers its kinetic and thermal energy to a turbine wheel, forcing it to spin at immense speeds. That turbine acts as a mechanical bridge. It connects by a solid metal shaft to a secondary compressor wheel. Moving to the intake side, because the wheels are linked, the spinning turbine actively drives the compressor wheel to draw fresh ambient air directly into the compressor inlet. Inside the compressor housing, the wheel aggressively squeezes this ambient air, violently pressurizing it into a dense state. This compressed, heated air is forced down through the compressor discharge. Because compressing air raises its temperature, it must flow through a charge air cooler to drop the heat and increase oxygen density. Finally, this cooled, dense air is routed directly into the intake manifold. The entire architecture creates a closed thermodynamic loop. It intercepts a waste product and converts it directly into a forced intake stream. The precise molecular goal of that compressor is simple: pack significantly more oxygen molecules into the exact same physical space inside the cylinder. The combustion math dictates that more oxygen allows the engine to inject a proportionally larger amount of fuel. This yields a massive boost in power, routinely increasing horsepower by 30 to 40%. Notice the difference in particle density in this visualization. At sea level, air is naturally thick and oxygen-rich, but as you move to high altitudes, the clustering drops off, leaving the air extremely thin. Standard, naturally aspirated engines inevitably lose power in these environments because they are physically incapable of drawing in enough ambient oxygen to maintain a full combustion cycle. A turbocharger mathematically neutralizes this altitude penalty. By mechanically forcing pressurized air into the chamber, it guarantees the required density regardless of the atmospheric conditions outside. For automakers, this creates an immediate manufacturing advantage: engine downsizing. By employing forced induction, an engineer can design a smaller, lighter four-cylinder engine that perfectly mimics the power output and torque of a large V6. Forced induction completely severs the link between an engine's physical dimensions and its power potential. However, generating this aerodynamic pressure introduces severe mechanical realities at the center of the turbo housing. The system operates under extreme thermal stress. Constant exposure to expanding exhaust gases pushes the turbine housing to a glowing red heat under heavy load. Inside that housing, rotational stress reaches its absolute limits. The central metal shaft linking the two sides operates at rotational speeds up to 250,000 RPM. This intense operational environment places an immense burden on the vehicle's engine oil and bearings. Any interruption in lubrication results in instantaneous, catastrophic friction failure. Beyond the mechanical strain, this architecture inherently creates a notorious dynamic penalty known as turbo lag. When a driver opens the throttle, there is a strict physical sequence that must occur. Exhaust pressure must build up, travel through the manifold, and overcome the inertia of the turbine wheel to spin it up to operational speed. That unavoidable time delay is the lag. The thermodynamic efficiency of the power loop is strictly counterbalanced by a brutal, highly volatile mechanical environment. This brings us to a central paradox. Modern turbocharged vehicles are heavily marketed for their fuel efficiency, yet drivers often experience extreme fuel consumption. The theoretical advantage is entirely valid. When you apply a light load to the pedal, a downsized turbo engine operates exactly like a standard small displacement engine, sipping fuel at a very low rate. The reality shifts under heavy acceleration. When you step aggressively on the gas, the turbo spools up, triggering the boost and instantly flooding the combustion cylinder with a massive volume of dense pressurized air. Look at this graph mapping the engine's response. Once the boost threshold is crossed, the engine control unit registers the sudden influx of air. To prevent the engine from running too lean and destroying itself, the computer must dump an equally massive amount of fuel into the cylinder, instantly tanking your fuel economy. Turbochargers do not guarantee efficiency. They simply offer the driver a highly volatile choice between extreme economy and extreme consumption. This split screen illustrates the immediate economic cost of manufacturing these systems. Bolting a turbo onto an engine requires a vast array of auxiliary components: intercoolers, complex wastegates, and high-pressure oil lines. When those internal components, spinning at hundreds of thousands of revolutions per minute, inevitably degrade or fail under constant thermal stress, the steep financial burden of replacing the intricate system falls directly on the consumer. If the system is this fragile, complex, and expensive to maintain, why is it the undisputed standard across the automotive industry? It is the only mathematical solution to a strict industry mandate. Automakers must balance intense consumer demand for high power density against rigorous government emissions and efficiency targets. The modern turbocharger is the ultimate engineering compromise. It is a highly effective manipulation of thermodynamics, operating constantly on the ragged edge of mechanical failure.